So let's begin jumping in. We've got today, we're going to talk about infinity. Infinity, again, it's going to be a recurring theme. I'm trying to prep you all with the concepts here. Again, the way that this class is organized is different than most calc classes. I've taken the time to really try to approach this class from a way that I think will best engage you all and get you understanding and excited about the material before it becomes just a series of notation. So we're going to try to give you, again, some more insight, some more skills, some more awareness around what infinity is, and we're going to introduce this idea of the method of exhaustion. The method of exhaustion, as it is in the name, is kind of promoting that we can talk about infinity just from doing the grunt work of considering larger and larger numbers. That's not excellent, but it is a pretty good place to start. We can just play with large numbers. The difficulty then is that we have to play with large numbers, and we have to do this in a recurring pattern. Once we find the pattern, however, we'll recognize there are other techniques. We can step away from the exact big numbers and go more towards their structures and behaviors and stories and work that angle. So I have a quote here. There are things which seem incredible to most men who have not studied mathematics. Very old quote from Archimedes. I think today we can absolutely replace men with just humans, because often mathematics is viewed as mathemagical, because people don't understand how it works. In the same way when we were talking about Gauss in the last lecture, where Gauss was able to add up all of the numbers between 1 and 100, that looks incredible. It must be a supercomputer. But once we had insight into it, it was actually a pretty easy pattern for us all to use ourselves. So it's not about the intimidation of the answer. It's about trying to understand the methods and have insight, kind of gazing into the soul of logic itself. So a story to help introduce this chapter. We're going to go back to some historical motivations, some of the first places and reasons why people were studying area. Now, if we go back to ancient Egypt, then we have a very interesting dynamic that occurs. Remember that ancient Egypt is the birthplace of geometry, right? It's a Northern African mathematics. So when we're talking about geometry, we have to figure out where it came from as a motivation. Well, in ancient Egypt, there was a desire by Pharaoh to build very large structures, incredibly expensive structures, which required, of course, money. Well, in order to get money from the citizens, Pharaoh would employ an age-old practice that we continue to this day. He's going to tax people depending on how much land they own, because that's a good representation of their ability to make wealth and their ability to have wealth. So therefore, we can ask them for more of that. Now, the reason why it might have come out of ancient Egypt and this practice is because if we explore different shapes, different regions we can imagine people having as properties of land, we start to recognize that if they had a square or rectangular plot, this is easy to estimate. We can create a rope with knots along its length. We can go along that length and determine units. And if we do that in both directions, we will get a number of square units. And that's where every square unit comes from, is us literally dividing a region into squares and counting them. That's what we're playing with. If it was a triangular region, a little bit more mathematics had to come into play, because there were some squares that were fully contained, but then it all of a sudden became an effort to find interesting insight into this. And so an interesting formula that we now have is recognizing that if we consider the height of a triangle, we can take one side of it and imagine flipping it over. So the base is cut in half, and we form a rectangle where I have one half of the base as one dimension, and I have the triangle's height as the other. Hence, we get the area of a triangle as 1/2 base times height. So we have a little bit of a creative play. The difficulty became with what are called curvilinear structures. Curvilinear structures where you have curves to play with, these are troublesome. There are regions where we can find completely enclosed square units. However, when you begin getting into the curved region, we don't really have the ability to estimate how big these are. We can guess, but we don't have anything perfectly accurate. On top of that, we can't even scale it down. Squares we can measure with smaller squares. Triangles we can break into triangles that we can reform and relate to squares. You can't fill a circle with circles. Little miniature circles stacked inside of a circle still is going to leave a bunch of gaps. So what's the approach for trying to measure curved shapes? And of course, we know that they're everywhere in nature, so this is a prevalent question, right? Especially if you're talking about commerce in addition to land. Now, an interesting thing also is playing off in Egypt. Who remembers what would occur every year in Egypt? What's something you remember back from your geology class or your global studies class? What would occur? Throw that in the chat. What do we remember about Egypt, specifically Cairo, and what would occur every year? Good chance for the history buffs to let themselves be known. What do we know about Egypt? Got a bunch of pyramids, Pharaoh. What else? Why was there a big civilization there? Nothing? No one? No one this morning going to be the history buff for me? All right, some more hints. It is next to the Nile. What do we know about the Nile? What occurs every year with the Nile? There we go. All right, thanks, Craig. I was getting a little bit worried here. I was going to have to send you all back and let all your teachers know that you've forgotten. Yeah, the Nile floods, right? We all remember learning about this. Nile would flood every single year. Well, now play that into this issue of trying to collect property taxes based on property size. If you put a property marker out on someone's land, and then every single year the Nile floods and removes that property marker, well, now you've got a situation where a bunch of homeowners were trying to place the property markers in different spots so that it looked like they owned less land, so it looked like they had to pay less money. Oh, well, you want to talk about a way that was going to like irritate Pharaoh. Yeah, people trying to skimp on their taxes, that was going to do it. So he had to employ mathematicians to find the size of these not easy regions as a way of really trying to make sure that people were paying their fair share in taxes. So that's exactly right. All right, brownie points go to Craig. Very nicely done. So we've got a very real incentive. We've got to find out the sizes of shapes because we have to reestablish property markers because it ties to money. And of course, we know that today, even in commerce, if we're trying to figure out how big something is before we sell it, that should be an important detail. Now, how did they do this? My favorite part of this story is that they did not have an answer. They didn't have an answer. As a civilization, for as long as the civilization was there, they never actually found the true answer. Because what they did instead was they found a good guess, and that was good enough for them. So any of you who are in the engineering track, you should relate to this story. Like for entire thousands of years, a civilization existed without knowing about pi. We now know pi came up to be the number used here, but they didn't have pi, not to nearly as many digits as we did at least. So what they did instead is they just made a guess. They just said, this looks like it's about a quarter, and it looks like it might complement with this, which is about 3/4, so let's call that 1. And they would go through the entire thing and they would have people professionally trained to be able to just make good guesses. And then people would be given a value and then those values would change just based on the people making a guess. Not an excellent strategy, but one that does kind of get the job done and usually isn't that far off. However, another way of doing it is that they would fill these shapes with objects. So you could imagine stacking inside of these objects a whole bunch of pebbles. And then they could take those pebbles out and they could count the pebbles. And that was a good way of being able to estimate how big these regions were. Or similarly, they would put a grid on top of it and then they would just simply count as many things fit inside of the grid, but they could make the grid smaller. By cutting these grid lines in half, they could find more rectangles, more squares that were inside of the region, clearly, and less that were kind of those ambiguous, I don't know cases along the edge. So we had this approach of being able to just make better and better guesses. And I like that. I like that that is a way that you can always begin mathematics. Then we have Archimedes. Archimedes is a Greek mathematician about 300 BC living in a coastal town of Syracuse nearby Egypt. And Archimedes, if I was going to try to label one as my favorite mathematician, it's got to be this guy. Like, he is just an absolutely incredible mathematician, because in addition to studying math, he's also studying engineering. Possibly you've heard of the Archimedes screw or the Archimedean lever. Those are things that he was popularizing at the time, but it goes so much further beyond that. This guy was building machines of war since he was 19 and discovering truths about mathematics that we continued to use for thousands of years afterwards. Because he was in a coastal town, that coastal town had a lot of trade, it had a lot of use and military importance, and so as a result, there were often quite a number of attacks. So this man had literally invented, and you can see it in a drawing here, a claw, a metal object that would reach into the ocean, grab a hold of enemy warships, and with two people operating it, pull those warships out of the water until everybody was shook off of it, and then dropped it onto the ocean so that it would split. Two people could take down an entire warship with a machine that Archimedes invented. On top of that, he is also credited for inventing a heat ray that used parabolic mirrors. We all might have learned in our algebra class that parabolas have a focus. Well, it's literally what they do to sunlight coming into them. As sunlight comes in, it concentrates that sunlight on a particular spot. That's why it's called a focus. And so by using parabolic mirrors, he could use and capture the energy of the sun and burn warships at a distance when they did not see any flaming material coming at them. So spontaneously, these warships would burst into flames and the enemy had no idea why. It's incredible ideas. And then we also have the original flamethrower that we can credit to Archimedes, where he would literally create a chemical substance that they could light on fire and throw at enemy warships. And those enemy warships would then burn, and it would stick to the warships and to the enemies. They couldn't get it off. It would float on the water, and there would be battles where the ocean was literally burning. And then there's so much more on top of that. He's credited for inventing the first cruise ship because he was able to find a way not of being able to create a big waterproof vessel, but in fact just recognizing that the truth to floating is actually just not sinking. So he created a very large ship and a way of removing water efficiently so that the ship was designed to sink on purpose, but if they could pump the water out faster than it went in, it would stay afloat. Very creative solutions, incredible. So if you're going to think about Archimedes, you can kind of parallel him to the ancient time Iron Man, because that's about literally what he was, right? Engineer, mathematician, creating war machines. Think of the arc reactor, right? That little thing in Iron Man's chest. There you go, Archimedes. You got a little mnemonic for you. If any of my fellow Marvel fans out here, y'all can see how big a Marvel fan I am. Y'all know what that is? It's an engineering drawing of the arc reactor in Iron Man's chest. So I've got a little bit of pull here, hopefully, with y'all. So let's talk about some of the approaches that Archimedes is playing with. Archimedes is now trying to help them with determining the size of circles, but Archimedes is not going to approach that from saying, I don't know where to begin and I don't know what it is, or I need to go find it. He's just going to try something. And that's incredibly insightful. He's just going to try it. He's going to recognize that if I'm trying to find a circle, I know that circle's area must be bigger than anything I can fit inside it. So I could fit a square inside it, and it's got to be bigger than the square. And I know how big the square is, right? If we say this is a circle with diameter 1, then that means that this diagonal length is 1. And via the Pythagorean theorem, we can solve for what the side lengths are. So we can calculate what the square is by just determining how big the square on the inside is based on its diameter of 1. Similarly, you could nest this inside of a larger square. So it's got to be smaller than the larger square, else it wouldn't have fit. How big is the larger square? Well, it's got to have a side length of 1 in both directions because it matches up with that circle. So that must be smaller than 1 square unit, but larger than whatever the area is for the inside one. And I'll kind of leave that one to you, right? We could do a little quick solution if I wanted to figure out what those side lengths were. A squared plus b squared has to equal c squared, where c squared was 1 squared. And a and b, since it's a square, have to be the exact same thing. So we could call that 2 of these x squares has to be equal to 1. Well, that means that the side length was the square root of 1/2, which if you rationalize it, you are all more familiar about saying that as square root of 2 over 2. So you multiply that by itself and you get 1/2. So it's bigger than 1/2 square unit and smaller than 1 full square unit. And you get to kind of play with this. But go beyond that. Archimedes discovered that what we could do in addition to using squares is we could cut at some of that region that's remaining and we can make that into a triangle. So we can cut into this region and find some more. And then beyond that, we can cut into some of the remaining region using triangles and some of the remaining regions using triangles. And this entire process he was able to use to be able to closer and closer approximate the true size of the circle. And similarly, on the outside, he could cut away some of this extra space and make it from a square into an octagon, and then make it into a 16-sided polygon, and then make it et cetera, et cetera. Now, in truth, he had one more creative strategy that was required. He didn't start with a square, he started with a hexagon. And if y'all are interested in his proof, it's in the guided notes. In order to get that proof for you in the guided notes, I had to pull down Archimedes' original mathematics, which he was working through using square roots with fractions only, because remember, they didn't have irrational numbers. And he's doing all of his math using Roman numerals because they did not have the Latin number or the numbering system we have today. And he had to do all of that using only the Pythagorean theorem. So I've got that entire thing rewritten for you all in the guided notes where you can follow it. It uses one formula and one formula only, no trig, no nothing. It is Pythagorean theorem, and it is beautiful. It is an absolutely gorgeous proof. I highly, highly recommend that as part of your practice and study for the course, you pull off those guided notes, and I've got it written for you. Your job is to just kind of try to understand it and go line by line and fight for the understanding of that proof, because that's part of mathematics, is just being able to understand some of this dense material that went behind all of the formulas we take for granted today. So you can start to see that this strategy of cutting and adding more sides to a polygon is going to make it better and better approximate a circle. And this is as far as Archimedes took it. He took it until there was 90 different sides, which again is an incredible amount of iteration and persistence. And he was able to do that by finding a pattern. But you can see that this is going to be very close to the true area of the circle. And this gives us insight into something we are going to use as a truth whenever we are talking about area for the rest of this class. Area, or what we will later call an integral, as a little heads up, area or integrals requires that we are starting with a region that can be bounded. So it requires that we are trying to find a circle that can be bounded with something that's a little bit bigger and trapped with something that's a little bit smaller. And all we're going to do is try to make that closer and closer to the truth so that it gets trapped between a metaphorical rock and hard place. That's what we're going to find the region, is the region is going to be the result of squeezing an unknown between two knowns. We'll later introduce that more formally and call it the squeeze theorem. So that's squeeze theorem right there. So by bounding, Archimedes was able to determine a value of pi that went out to a good number of decimals, right? So we got 3.1514 was about what he got, which again makes sense that it didn't go on forever. They did not know about irrational numbers to a large extent. And this is something that can be represented as a fraction. 31514 divided by 10,000, right? Sorry, 10,000, because that ends in the 10,000th place. So we can represent this as a fraction. Fractions, the Greeks and Egyptians were comfortable with. It's part of the rational numbers, so they're good with treating pi as if it's pretty close to a fraction number. We now know, using supercomputers and other approaches like it, that we're able to continue to get more and more refinement on those decimal places. But these, again, were calculations done with Roman numerals and fractions only, no irrationals, and square rooting by hand. Like, it's an incredible, incredible feat. Now, truth is that if we're going to look historically for where the first accurate estimates of pi were, a similar value had actually come out of China about 500 years later. But I think that both probably deserve equal credit since there was no communication between the regions at the time. So we do have a bunch of different people trying to follow and find this interesting answer because it's prevalent. Another interesting point that you all might not realize is that this value of pi was used as the value of pi until about the 1900s. This whole idea of like whatever our calculators currently display, 3.14159265358, like going on forever and ever and ever and ever and ever. Yeah, that's not what was used. That wasn't what was known. The computational power it took to find the next digit of pi got exponentially harder. So 5 decimals was a pretty good number, and it got a little bit more refined after that, but we didn't have our understanding of pi until the computer was invented, which was decently recent. So this is something that Archimedes literally found the value of pi that we continued for 2,000 years. All right, so let's talk a little bit about here. We're going to go back to this idea of infinity. Notice again that the idea of having a number that you can't touch is challenging, that you have this pi value that goes on forever, but we're supposed to still say that there is a number at the end of that we're locking that down. That's a contradiction. We're going to say there's a number there. We're going to say, what number is it? They're going to say, I can't describe that number to you. And they're going to say, well, how do you know it exists? And you describe it not by what it is, but by how you got there. And this might sound weird, but it's actually something that we do quite a lot. Like think about the square root of 2. What is its value? What is the square root of 2 as a number? You might say it's about 1.7-ish, and it's like, good, but what is it? It's about 1.7-ish. What is it, though? You're like, it's the square root of 2. It's like, exactly. It is a number that we are describing as a story. It is the number that would have resulted if we could effectively square root 2. Like, that's why we call it the square root of 2 as its identity. It's by its buildup. And sometimes that's going to happen. We also know this goes on forever, but how do we know this? Well, I showed you a proof for the square root of 2 being irrational before. It took a while for people to be able to prove that pi went on forever. If you're interested, I would consider looking that up on Google. It's to find that it's a transcendental number, that it's a number that continues on forever, is a very interesting proof. Again, one that I think was completed in about the 1900s. We also need to remember that we have 0 because we're going to start playing with both of these in tandem. 0 is not a simple number. It's a familiar number to us, but in truth, it was scary for many cultures for thousands of years. Theologically, it was a challenging number for people to accept because you had to understand that 0 corresponded with nothing. And in a church-run state, the idea that God was everywhere and pervasive was a common belief, and thus there should be no such thing as an absence. There should be no such thing as a nothing if there is a God that is everywhere. It became a challenge. It's also why out of the Middle East and India, 0 was first invented, because if you look back in their religious context, there are plenty of gods that have a duality, a paradoxical nature to themselves, where they are both being and not being, there before and there in the during, death and rebirth, the cycle, reincarnation. All of these ideas were perfectly well accepted, which allowed for 0 to be something that was more easily promoted and explored. But mathematically, can we touch 0? Like, have we ever touched nothing? Can we draw it? How do we draw it? In fact, even its symbol, even this symbol is literally trying to represent an empty hole, like in a Mancala board. So we've got like an absence. We're just trying to recognize that we can do that. Even children, if you try to teach them about 0, you have to teach it to them indirectly, right? You don't start with, let's all learn our counting numbers. Ready? 0. Let's begin now. 1, 2. We have to start with 5 fingers, and then we have to almost count down in a backwards nature so that they understand that I've removed things, that it's a process that got me there as opposed to just recognizing it visually. To show you that the 0 value is a little bit difficult to conceptualize, this is where we're really going to start to get into some fun stuff. Here's a question for you all. You ready? You ready to throw your answers in the chat? This is going to be a fun one. Imagine that this is the task. I would like you to walk halfway towards a wall. So find a wall in your room. If I was in person with y'all, we'd do this demonstration live. So find a wall. Imagine I'm going to ask you to walk halfway towards it. And then I'm going to ask you to cut the remaining distance in half, right? And then another remaining distance in half. You're getting closer and closer, cutting the remaining distance in half each and every time. The question I have for you is, will you ever not get close to the wall? Will you ever reach the wall? Oh, we got a lot of no's. Well, 3 no's. Where are the rest of y'all? Come on, it's Thursday. Wake up. You don't get to be tired until Friday. And then Friday, you got to wake up because you got a party. All right, we got a bunch of no's. Oh, we got 1 yes. All right, y'all ready for this? I'm going to try to do this demonstration here. I got to move my webcam. All right, this is my wall. Y'all see my wall? I'm not going to get up and move because I'll move away from my microphone. Imagine that this pen right here is the me. Ready? It's going to cut half the distance. It's going to cut half the distance remaining, et cetera, et cetera, et cetera. You ready? Now tell me that that pen didn't hit every check mark. In order to have reached the wall, it would have had to cut the distance in half and cut the distance in half and cut the distance in half, et cetera, et cetera, et cetera. And it made it to the wall. So what's going on there? I'm waiting for those with the greatest opinions to throw things in the chat. See, what we have is we have a little bit of a paradox. We have a paradox that says, if you do this forever, some of you may say that there is something left. And it's like, okay, well, how much is left? And then you say, well, there'd have to be this much left. And I say, well, if there's this much left, then you must not have done it forever. Because if you had done it forever, you would have eventually got smaller than that. So we got this weirdness that's occurring where it's this idea of forever competing against something left. But at the moment you try to tell me what's left, then you've violated the pure definition of saying you did this forever. We've got a paradox here. To give you a quick example of that, let's play with something that's a little bit more on the paper. Here's one for you. Does 0.9 repeating equal 1? And again, we've got to be careful here. I'm not using the equal sign lightly. I'm using it for its mathematical purpose. I am not saying close to 1. I am not saying almost 1. I am saying is exact, the same thing. Are these the same thing? Well, you think on that one. Okay, so I got something from Craig. Would it have theoretically taken forever to reach the wall? It didn't for the pen. So the trap becomes, if you're talking about there being a certain amount of time that it takes you to go each of those periods, and if it takes you too long to do each of those, like if I all of a sudden I take a break and then I take a sip of water and then I walk over the remaining distance and I take another sip of water, yeah, that's going to take me forever. But if it keeps taking me less and less time, like it would for the pen, then it reaches no problem. So again, there's kind of there's things to consider. Just the process of forever does not mean that it's going to result in a forever big result. All right, so does it work? Ooh, we got some competition. All right, let's play a little bit here. Let's expand this out. Here's the preface. I promise you that nothing I am doing on the paper is incorrect. There's nothing here that I am like holding the wool over your eyes. There's no cutting corners here. I promise everything I'm about to put on the paper is mathematically legitimate. If you have questions about why I did or how I knew or what I wrote, that's totally fine. Just I want you all to understand, like, I'm not tricking you here. This is all legit. So let's expand it all out. We got 0.9 repeating. Let's go ahead and write that out a little bit. 0.9999999999999. If we're not convinced this equals 1, that's fine. I'll put a little question mark up here for right now. Let's call it something else. Let's call it X, shall we? We'll just give it a label. What's it equal? I don't know yet, right? We'll just call it X. Now, I can multiply both sides of an equation by a number, and I don't change the truth. So I'm going to multiply both sides by 10. That's going to make this 9.9999999 repeating. And on the right-hand side, I will have 10x. We all feeling good so far? Give me a little nod in the webcam. Maybe give me a thumbs up in your reactions. We all feeling good? I can do this, right? Okay, cool. Here becomes the fun part. Ready? let's go ahead and take this equation and subtract it from the other, which I can do because even though it looks different on both sides, it's the same thing. And all the equation means is that it's balanced. So if I take away the same thing, it doesn't matter if it looks the same or isn't, it just is the same value. If I take that away, it still should be balanced. Well, in doing that, I can just do long subtraction. Let's do 9 minus 0 is going to be 9. Let's do 0.9 minus 0.9 is going to be 0. And then I do that for the next one, 0 and 0. And I should have zeros all the way on down the line. And on the right-hand side, I have 9x. Well, I know that 9 followed by forever number of zeros is 9. So that means 9 is equal to 9x. And I could divide both sides by 9. That's x is equal to 1. So that means that x is equal to 1 and x is also equal to 0.9 repeating. So 0.9 repeating must be 1. Who here is feeling bothered? Because this should bother you, right? This is bothersome. It's okay that it's bothersome. But in fact, it is true. It is true. I'll hit it from a few different angles to help give you an idea of what's going on here. Because what I'm playing with is that we can have something that looks incredibly different, but means the same thing. This is something that you have used before. So let's just remind ourselves that this happens in math all the time, right? This looks very different than this, but they are the same thing, right? So we do have times where things look different, but mean the same thing. This is another one of those cases. But to conceptually understand this one, it's a little bit harder. So let's try a few different angles. Maybe if you're feeling bothered, you're going, but there should be something left. Right? There should be something at the end of this, some forever small value that is left over as a result of this. And it's like, great, that's my instinct too. Let's play. Let's play into that idea. So let's go ahead and play with this one here. Let's imagine there is a difference. Let's imagine there's a difference between them. How big is that difference? Well, it would have to be a forever small thing. Right? Like you have to be a zero, like a whole bunch of zeros, and maybe there's like a 1 at the very end of that, right? A forever number of zeros and then a something. Okay, well, let's play around with that. If we define this to be the case, that we will call D the value that is zeros, a forever number of zeros, and then a 1, then let's play. Okay, I'm going to go ahead and then multiply both sides by 10. So I should have 10 of these little differences is equal to, what would it be? It'd be 0.0000, a forever number of zeros, and then 1. Right? If you want, there are some zeros after that, maybe. So we could play with it this way. Maybe if that's not what we're feeling, we could do it in the other way. Maybe it'd be easier to do it like this. Let's divide both sides by 10. Let's divide both sides by 10. And then we would have a little 0 right here, right? We'd move the one more smaller. So now we got a forever number of zeros, but also one more 0 and then a 1. Well, a forever number of zeros and one more 0 is still a forever number of zeros. Like this, by definition, is D. So that means that D is the same thing as D cut by 10. Well, then I can multiply both sides by 10. That means that D is equal to 10 of the D's. And I could divide both sides by D, and that means that 1 is equal to 10. Well, we know this isn't true. So this must not be true. So this must not be true. So this must not be true. So there we are. That must not be true. Because the later statement is a direct result of the earlier. So if there is a number at the end of all of this, it does not seem to be a real number. It does not work with the operations that the other real numbers work with. There's this idea that there's a forever small positive value. What number would that possibly be? Because not only could this be a proof that creates by 10, I could have divided by 100. And if I divided by 100, that just still would have had the same argument, and I would have been able to prove that 1 is equal to 100. If you divided both sides by 5, that would have made it a 2 at the end of all those decimals, and then I could have been able to show you that 1 equals 2. I could show you that 1 equals anything. I could subtract 1 from both sides, and then I have zeros, the same thing as 99. Like this entire, like it doesn't work. And this isn't about algebraic intimidation. It's about recognizing there's a story behind this. The story is the act, the definition of forever approach prevents you from saying there's something left. Because if you say there's something left, then you must not have approached forever. That's the insight from all this. Literally saying forever approach implies that you got there. They're identical in meaning. Forever approach is the same thing as is. Okay. Let's recall that we also have a few different examples of that, right? We played around with like the whole what is 1 plus infinity or 1 minus infinity. If we say that that's infinity, that doesn't really work. And again, that's because you don't, like, once you have the forever approach, 1 more than forever doesn't make any sense. It's part of the original meaning. It implies you already got there. So we have paradoxes that happen if we start to play with these ideas too loosely and using the things we're familiar with. So as we can see, forever is not a simple idea. Having nothing left is not a simple idea. Thus, the infinite and the infinitesimal, that's a new word for y'all, infinitesimal, that's the infinitely small, the forever small. These are not simple ideas. We do not play with them directly. We play with them through the stories that got us to them. Okay. Right. This one right here, broken proof of 1 equals 0, having there be a forever large real number. If that equals infinity, we subtract infinity from both sides, 1 equals 0. Nope, nope, so nope. So better conceptualization. Infinity, you can think of it as a number. It is a number, but you've got to make sure you're qualifying that. It is not a real number. And I don't mean realistic. I don't mean can't be found out in nature or doesn't have any purpose in our thought process. I mean, it doesn't belong in the real number line, the number line that is built up of rationals and irrational numbers. It's something else. You can think of it as a transcendental number. You can think of it as a number that is part of the infinite. I like to think of it as a boundary that helps me give something that's nice and easy as a reference, where I have the real number line, and then off of the real number line is infinity. And similarly, any talk about an infinitely small difference, d, is not going to be on the real number line, right? It doesn't exist and work with those definitions. So it's not on the real number line. It's something off the real number line. It's something that is different and not part of our normal number structure. So infinity is a boundary. Infinite, or the infinitesimal, is a loose conceptual idea at best. Okay. So moral of the story, do not plug in infinity. Again, this is my reminder. This is, I think, the second reminder. I'll probably give you some more throughout the semester. If I see you plug in infinity in any problem ever, I will zero out your credit. It doesn't make sense. Don't cut the corners. It doesn't work that way. You cannot plug in infinity ever. Ever, never, 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 ever, ever, never, never. Can't do it. Don't do it. Doesn't work. If you have taken calculus before, you may know that sometimes we play with a similar idea, which is this idea of what about increasing towards infinity, right? So we've got this idea of like x going towards infinity. I understand where this is coming from. It's coming from that exact same model I just drew for you, where you have the real number line and kind of the boundary that's off the right-hand side of it. So that makes that kind of get where that's coming from. I will forgive that language, but that language should be noted that it's also wrong. That's wrong language. The idea of x towards infinity, how would you prove that? Because I could talk about getting towards 100 from 0. I can get towards it because I know that 10 has a smaller difference. I can do subtraction and see that that is 90. And then I can go to 20 and see that's a smaller difference. Like I can prove that we can get towards real numbers. So towards is fine. How do you prove that you get towards infinity? Is 100 closer to infinity than 10? Prove it. You can't do subtraction. What are you going to reach for? So this idea of towards doesn't make any sense from a formal standpoint, but I do get the idea. So what you want to think about instead is just there's small changes in language that really are the game we're playing here. Instead of towards infinity, what we really mean is x increases without bound. Do you see how that's the same idea? We want to get this idea of x getting bigger, but by saying x increases without bound, it keeps me in the real number line. I can prove that 100 is bigger than 10 is bigger than 0. I can prove that 1,000 is bigger than any of those. I can prove that things are bigger. But to say that's getting me towards infinity, the moment you bring infinity in, oh my golly, you got to be real careful. It's not an easy idea. Don't treat it simply. It doesn't work that way. So be very, very careful. We're talking about increasing towards. So this is going to be a shorter class. I'm going to end it at about this point with a little preview for the next one. I'm going to do that on purpose because I want you to take any extra brain power that I give you as a result and go look at the guided notes. The guided notes have that really big, dense proof from Archimedes, but it's so insightful. It's so creative how much he was able to do with one Pythagorean theorem. Like, it's just great. And it's easy to kind of look at the picture. I know it was for me to look at the picture and say, oh yeah, sure. Like, we can make a polygon get close to a circle and then find some numbers for that. I'm on board. Look at the proof and you're like, oh man, that took a while. There's a reason he's famous. Like, it's a big thing. And it's really cool to be able to see into the past, see into someone's brain like that. So for next class, we're going to talk a little bit about how do we do these calculations that last forever. You were all kind of talking about that, right? An example would be if I have that pen moving closer and closer to the wall, then I first had it cut half the distance, and then half of the half remaining, which would have been a quarter, and then half of the quarter remaining, which would have been an eighth. So this is a way we could have represented the travel that my pen or we did moving towards the wall. Well, how do we prove that that equals 1? Because it does equal 1, as I showed with the pen. The pen got there, and it got there through a series of addition. So there must be a way for us to prove that this is this, not gets close to is this. So we'll be able to talk about what's infinite division, infinite multiplication. And we're also going to do all this through E. E is Euler's number. It's one that you've probably seen come up in an algebra class before, but maybe it was just something that appears in logarithms and practice problems. I'm going to give you a storyline that makes sense of E, a very applicable business storyline that's considered to use or continued to use today. Very, very useful stuff. So if you have any questions, stick around. I'm hoping some of you who still have your minds blown will be able to talk this out with me. We'll get some nice solidification of ideas. Otherwise, I'll see you all tomorrow. We got a quiz. Don't forget.